So I'm curious, not related necessarily to the technology, is there a story behind the name 9T Labs?
Oh yeah, I was waiting for that, Sharon. I mean, we come from a technical university. We have technical backgrounds. So the 9T is our processing, the degrees of freedom which we have on the processing side. The T is actually this out of plane orientation of the fibers, which is for some applications super relevant, and the T stands for it. And the labs we added to it because 9T was like looked too short for us. So that's why we added the lab. So, but actually, a lot of people call us 9T. So it's especially in the US, a lot of people call us 9T. So there's a very technical explanation for the 9 and the T and where it stands for, which is nice because it shows where we come from.
Gotcha. All right. So what are the primary challenges and or limitations associated with AFT? And then how are these overcome?
Mm-hmm. It really goes back to the fundamental question about the composite manufacturing and like what's limiting the adoption there, or what are the challenges there. And part of the challenge is that there's a lot of, it's very fragmented, very different technologies, very different vendors. And the first point is being a solution. So having all the different elements from an idea to the final produced part, and also scaling the part in production. So being the solution, having a solution rather than like one element, just the software, just the hardware, just the polymer materials, the composite materials. So that's one. And the other part is really like the software capability, as we just talked about, that you have. It's such a complex material and engineering material. It might be one of the, if not the most complex. That means also it has a lot of opportunity, but especially if you orientate the fibers in a very optimized manner, which really is what you need to do to get a structural and optimized part. It's beyond just engineering know-how, what you could learn, because sometimes it's too hard to grasp. It's just too sophisticated, the problem, that you can just make a good judgment call by engineering know-how. That's why it needs very good and validated simulation tools to simulate that, to optimize, to validate that the requirements are fulfilled. And that's a key challenge because you need good material data cards, you need validated simulations. There's many applications have many different problems. So it's very complex, but you have to capture this complexity in software. That's going to be a key.
So what do you see next in this realm? And are there any advancements or breakthroughs that you foresee? And then how might these developments reshape the landscape of 3D printing and additive manufacturing as a whole?
Mm-hmm. Maybe to the second part of the question, which is like, the breakthroughs that our breakthrough for the industry, basically. And as we all know, 3D printing had already different hype cycles in a way. It's not one different, and we're actually in one right now in a way to a degree. It's who breaks into series production. Everyone talks about series production, scale production, and what this means is like a little bit like blurry sometimes, because okay, end use parts, but end use parts could mean a lot. When I talk about this, for me the most important part is that we have a technology stack that produces parts at scale. That means also not necessarily for 1 year. So you have one engineered part and you produce it. It could be up to 10 years. You produce this part really at scale. And I come from metal manufacturing. That's where I originally come from. So that's what we have in the metal world. So CNC milling, CNC turning, this is how this works. And we need a technology and the right applications in the additive realm that also has the goal of producing parts at scale and not doing prototype jigs and fixtures and this kind of applications, which is a very limited market. It's very hyper competitive, and it's part of the struggle the industry has when we talk about 3D printing right now. And we are from the start are focused. When we started 9T Labs about 6 years ago, we were from the start focused on producing parts at scale. And that's also the combination of additive and the molding and the applications, not just doing 50 parts or one part. It's not one-off mass customization. It's really about making a great engineered part and producing it for the thousands of 100,000 times. I personally are very excited about like applications which we also have coming out. Because it's always so hard we cannot show applications until they're fully engineered, fully proven, and the customer is launching them. But for me, it's a very interesting time when where we see applications coming out with customers, and this will change also the perception of what we can really do, because it's sometimes so hard to explain. We can talk about software, we can talk about the hardware, we can talk about the materials, but you really see this super high strength material in an application and you can feel it, then it's different. And so that's what I'm very excited about, and I'm looking forward to talk more, to customers and just like people that are interested in the field to see to show what we can do with composites, because composites been around for 70 years or more. It depends who you ask. And we are not using this high performance material in a high performance way. And what we are doing is really like we're adding this high performance, using it in a high performance way to the high performance material. And it's very exciting what we can do with this kind of super strong material and lightweight material.
Can you give me some examples maybe of what you're talking about, and then also some examples of what you envision?
Maybe two things, like what I'm seeing and what I'm very excited about, like one more application, the other one more technology wise. Maybe you can start on the technology side. On the technology side, I'm very bullish to see the evolution of the software stack, like how intuitive and how easy to use the software can get, even for a very complex material or very complex engineering task. So that's going to be very important for the adoption and enabling engineers in the field to do this, because we are not a contract manufacturer. We want to enable the industry, other people to use the technology stack. So that's what I'm very enthusiastic about to see, and this will also evolve over the years. On the application side, it's like, for me, it's like at this point in time, I cannot share the customer applications, but what we will see is that we really make a big difference compared to the baseline, meaning like the baseline being a metal part or could be also composite part, that we see an improvement that's not just like incremental, like small, like 5%, 10%. We see like 50, 60% improvement in performance. So in terms of performance over weight, which is very exciting to see. And just to give also just an idea for the audience that might read this or listens to it. I mean, we have composite materials that are like 2,500 megapascal, 3,000 megapascal. This is compared to metals. This is really a couple of factors of even in the strength, not just the light weighing. I mean, it's like you're half the weight, but you're double, triple, even 4 times the strength. But it's not used traditionally in the right way, because we're using a lot of fabrics, what we're all wearing. That's where this comes from, textile industry. But orientating the fibers in an optimal way, you can really see like how much performance there is still to be captured. And this is what I'm very excited to see if we can show this publicly, demonstrate this in the applications with our customers. So very excited there.
Can you tell me a little bit more about the sustainability factor?
Mm-hmm. That's also a good question, because it's in general, like in composites, again, been around for a while, many decades, and it's always a big topic. And you see most companies have some kind of green leaf on their webpage or on the presentations. This is generally, it depends on how you look at it, but there's certainly a factor that we have to deliver on the promise of sustainability and really like make good life cycle assessments or analysis and compare this to baselines and so on. So in general, there are 2 categories of polymers. There's the thermosets and the thermoplastics. One is the one that once you heat it up again, once the part is final, it just burns. And the other one is like, it gets moldable, it gets pliable again. So that's the category of material we are using. We're using this because of the processing route, but at the same time, it enables us also to multiple time reshape, remold the part, remanufacture the part. So this is where we can close the circularity loop. And we do actually quite a bit of life cycle analysis, but at the same time, also we're doing a lot on feeding back the end of life part or the end of life material back into the circle or back into the manufacturing value chain, so closing that circularity loop. And we demonstrated this a few times already publicly with brackets. I don't have the bracket now in my hand, but where you have a bracket that's made out of the same bracket and it has the same mechanical characteristics, but it's more than 90% recycled. And that's very, very important. It's close to circularity loop. It significantly reduces up to actually more than 90% compared to a metal part. You can lower the CO2 footprint. Not even talking about the mechanical and the performance side of things, just like the CO2 footprint. And at the same time, it has actually quite a bit of a cost impact too, a positive cost impact, because a lot of people sometimes recycling is expensive, and it is actually true for some some approaches, but the way we approach it is the recycling has a clear cost benefit. So that's a very big plus. And in general, customers ask for a solution that has an end-of-life solution. When you enter now with a new technology stack to market, I personally feel this is in manufacturing, this is a given that you have to have an end-of-life and a good end-of-life solution and a good understanding of the CO2 footprint.